Hello, everybody. Today we're going to learn about the concept of power. Power, say. With great power comes great physics homework, as the saying goes. What is power? When you get into a physics classroom, this is our last topic in our study of work and energy. What does it mean to talk about something being powerful? So if you get your note sheet, you can follow along and fill these in. Symbol for power is the letter P. No big surprise there. Often we use a capital P. Power has to do with work and energy, but it is a measure of the rate at which work is done. How quickly do you do work? How quickly does energy change from one type to the next or go from one place to the next? So it's not just a matter of how much energy goes or moves or is used, but how quickly that happens. So here's our big picture for the unit. Going back and reviewing our basic idea, we draw an imaginary box around an object or collection of objects. We make that our system. Our strategy is that if there's anything that has a potential energy associated with it, a conservative influence like gravity or the force from a spring or a charge, we bring that into the system. And then my non-conservative forces are in the environment, and they're able to do work. And work is a two-way street. It can be adding energy to the system, or it could be subtracting energy from the system. Systems have energy, and we've got kind of our two main flavors. We've got potential energy, energy that's stored up due to our conservative forces and influences, and kinetic energy, energy of motion as physical stuff moves around. So power is used to talk really about two things in this diagram. As a measure of how quickly either work is done, energy comes in and out of the system. And so we're going to add this to our equations here. The average power is equal to work divided by time. It's the work per second, or the joules per second. And so that's referring to, like, if you're sitting here watching this flow of energy going in and out of a system, it's how quickly that energy is moving in or out. But we can also use power to talk about the rate at which energy changes inside of the system itself. Because it's possible that no work is done, that no energy goes in or out of the system, but we might have like a ball that's tossed in the air, and it's all of its speed gets turned into height, and then it falls back down and it gets turned back into speed again. So what this represents is energy in the system changing from one type to the next. And you can use power to talk about how quickly that change happens, just like you can use power to talk about how quickly energy comes in and out of the system. Either way, it's a measure of work or a measure of energy divided by time. So the unit of power is the joule per second. When we give this a name, what do we call it? Well, what do we call it? It is called the watt. And we abbreviate that with a capital W. So a watt is a joule per second. It is the metric SI unit for power. So we're going to put this down on our equation card. You can go ahead and pause the video and add it to your card. Power is work over time, and it's also energy change divided by time. It's joules per second. Just so you know, sometimes you'll come across powers that are measured in watts. A lot of devices, maybe like a microwave oven might be measured in watts, and it might, a 900 watt microwave is taking 900 joules of heat and creating it out of 900 joules of electricity every second. A 1,000 watt microwave is creating more heat energy every second than the 900 is. So it's going to heat your food up faster. The English units for power are English units of work. So instead of the Newton meter, it's the foot-pound per second. So if we're using English or imperial units, a foot-pound per second is what's called a horsepower, which has agrarian roots there, and it's labeled HP. And sometimes you'll see things, machines rated in terms of horsepower. Maybe it's the engine of a car, or maybe a power tool that you buy. Again, more power just means it does work faster. It generates energy more quickly. A horsepower is the same thing as 746 watts. So a 900 watt microwave is only a little bit over a horsepower. So horsepower is takes a lot more power to have a lot of horsepower than have a lot of watts. Those are our units. So one other useful form of this equation we'll add to our card as well is we can relate this, the rate at which we do work, to how fast things are moving. So I was just kind of thinking about this the other day. I was using the rowing machine here at school. And if you ever used a rowing machine before, it gives you all kinds of data about, how far you've rowed or how quickly you're moving. But one of the screens actually told me the power that I was generating, how quickly I was putting energy into this machine. And power is good, right? The more power I generate, the more quickly I'm burning calories, the maybe more benefit I'm getting from the exercise. And I was thinking about how this was done. If we look at this guy pulling on this, we know that work is happening, right? Because he grabs this rope and he pulls on it and he applies a force in this direction. And as he does that, the handle of the rope, the point of application of the force, moves through a distance. So he pulls at a certain distance with a force. And they're parallel to each other. If he pulls to the right, it moves to the right. So it's a 0-degree angle between the two. So we could actually calculate the power generated by pulling on this device. Think about what that means. Power is work divided by time. That's how quickly he's doing this. Work is FD cosine of 0 degrees. So it's FD cosine of 0 divided by time. And this is the same thing. Cosine of 0 is just 1. This ends up being the same thing as force multiplied by distance over time. Okay, that the FD is the work, and then dividing it by the time is the power. But distance over time, that's just how fast the guy's moving. That's his speed. So something that's powerful, is able to do work quickly, is also able to apply a force at a very high speed as it does work. And I can write this in terms of power as well, that power is force multiplied by how fast that point of application of the force is moving. P equals F times V. So let's add this to our card as well. These are going to be the last formulas that we're going to put onto our card, the equations for power. And a little asterisk next to this, it's assuming, and we assume this in our derivation, you can see here that the F and the V are in the same direction. So if your force is 90 degrees to your motion, then it's not doing any work at all. There's no power related. Okay, so that's it. That's power, and in terms of its how it's related to work and energy. We're going to do 3 example problems, and we'll see how power can be used to calculate different things in real life. So if you flip your page over, it's just one page front and back. We've got our 3 problems. So the first problem is about somebody climbing the Empire State Building. And I'm giving you the mass. That's about the mass of a 150-pound person. That 381 meters is the height of the building from street level to the top of its observation deck, and you can climb steps. I went on their website. It said on their tourist bureau that they recommend taking an hour to climb the steps, which is a long time. And so I'm curious, how much work does somebody do, and how much power do they generate climbing the stairs in an hour versus the world record for climbing the Empire State Building stairs, which is just under 10 minutes, 9 minutes and 33 seconds. So we're going to compare those two. So as is my wont, I will start by drawing a picture. Never go about solving a word problem without drawing a picture first. It's a bad picture. And we're going to try to identify what's going on here and what we know. So we know the height of the building. And remember, whenever we have heights, we have to pick our height of 0. So we'll make that be the bottom of the building. You could say the top here is the 381 meters, height of the building. And then we've got our person, so not really a scale drawing here, but our mass of 68 kilograms. And this fellow is going to climb the building. And he may climb, back and forth, left and right, but he's going to work his way up to the top of the building. He's going to be gaining some potential energy as he goes up. Okay. So how much work does it take for him to get up to the top of this building? So for part A, he's going to do it in an hour, and we got to find the work and the power that he generates. So to find the work, what I'm going to do is I'll use my energy conservation equation. We'll look at energy he starts with, we'll look at the work that's done to him, and then the energy he ends with. And in this case, think about somebody climbing the Empire State Building. At the bottom of the building, they will be standing still before they start. Okay? And then when he's done, when he gets to the top, his speed at the top is going to be 0.2. Otherwise, he's going to run right off the edge. Okay? So there's not going to be any kinetic energy at the beginning, and there's not going to be any at the end. So at the bottom, he has no height and no speed. So he has no energy at all. Okay? Then some work is being done. And when he gets to the top, he's going to have some gravitational potential, MGH. So the work done is simply the gravitational potential energy that the guy gains. He doesn't end up gaining any kinetic energy, he just gains height. And this work is done, it could be done by anything. It could be done by the elevator if the elevator lifts him up. It could be done by a jetpack if he gets up by a jetpack. In this case, it's being done by his legs as he walks up the Empire State Building. So we can figure this out. MGH, 68 kilograms is his mass. Empire State Building is on the Earth, so we'll use 9.8, and then the height is 381 meters. So we can solve for how much work he has to do to climb the Empire State Building, and it's a decent sized number. It's 253,000 joules of work to get up there to the top of the Empire State Building. Now, joules is just one unit you can use for energy, so maybe you're interested in knowing the exercise benefit of climbing the Empire State Building. You can convert joules into kilocalories, which are how scientists measure the energy stored in food. And this ends up being, surprisingly, 51 kilocalories. So, that is about half the calories in a banana. So all that work to climb the Empire State Building, and essentially you only need half a banana to get you to the top. That's kind of interesting. So that's the work that he does to get to the top. How about the power? Power is related to how quickly he does this. So in case A, and he does it in 1 hour. So power, we'll use power as work divided by time. So he does 253,000 joules of work, and he does it in 1 hour. Now I have to be careful with my units. 1 hour needs to be converted into seconds. So I'll multiply by 60 to get minutes and 60 again to get seconds. So it's 3,600 seconds. And the power required for this guy to walk up the Empire State Building, basically to take an hour to get up, is 70 watts. His body has to convert 70 joules of chemical energy in his food into potential energy every second. So that's the rate at which his body is consuming energy or metabolizing energy climbing the Empire State Building. And that's true for his body. If it's the elevator lifting him up, that's how quickly it has to supply electrical energy to run the elevator motor. So then what changes if he sprints? So this should be something maybe more impressive. We've got our world-class athletes. There's actually a competition every year in the Empire State Building to sprint to the top. And the world record is 9 minutes and 33 seconds. So the first question is how much work and then how much power. And the deal with work is that when we look at how we calculated work before, it was just the potential energy that he gained, and it had nothing in there about whether he took an hour or 9.5 minutes to get to the top. So it's actually the same amount of work. The exact same amount of work is required to get you up to the top of the Empire State Building, regardless of whether you run or walk. You're just going to burn off half a banana, apparently, in both cases. So then how about the power? That's what's going to be different. Power is work divided by time. We're going to try to do this in a much shorter time. 253,000 joules of work and 9.5 minutes. So 9 minutes and 33 seconds to be precise. So 9 minutes, I've got to multiply that by 60 to get seconds. Then I have to add the 33 to it. It ends up being a total of 573 seconds. It's the world record, which is a really quick time to get up to the top of that building. And it comes out to be 441 watts. So the world-class athlete is metabolizing food at a much faster rate than somebody who walks slowly. And if you're wondering, hey, it takes the same amount of energy, and that amount of energy seems kind of ridiculously small, I'll bet the exercise benefit is a heck of a lot better than half of a banana for climbing the Empire State Building, even if you walk it. Okay? It has to do with the efficiency of the human body. When the human body tries to do work very quickly, when it tries to generate a lot of power, it turns out that the human body is, we say, inefficient at doing work quickly. And that means that if you had a perfectly efficient body, all you would burn is half of a banana to do the work. But when you try to do work really fast, and I'm sure you know this, if you try to run upstairs, you're going to start to sweat, you're going to start to get hot. That's heat energy that's being produced in your body. That's wasted energy. And so you do overheat, and you do get hot, and you do get sweaty, and you start to shake, and energy gets wasted. And in fact, you're going to burn a heck of a lot more than 253,000 joules. You're going to burn off bunches and bunches of bananas sprinting to the top of the Empire State Building. On the other hand, The human body is very efficient at doing work slowly. In fact, humans are sometimes called endurance predators. And humans can basically outrun other animals like deer or antelope. They can run longer and farther. As long as you don't go too fast, you can continue to metabolize energy for long periods of time, longer than most animals and organisms can. So you probably aren't going to get hot and sweaty if you take a whole hour to get to the top and you take your time. And you're going to end up burning a lot less energy. So maybe your true energy expenditure might be a lot closer to this number than it would if you sprinted up. Not to throw too much biology in, but when your body is just existing, there's something called your basal metabolic rate. Your basal metabolic rate is the rate at which your body is consuming energy just to stay alive, to maintain homeostasis, to keep your heart beating, keep your body temperature where it should be. And that's based on your age and your physical condition. There are online calculators for these things. And I calculated for myself, a 43-year-old man, that it comes out to be about 86 watts. So if you think, wow, I'm just sitting here in the chair doing nothing, I'm consuming this much energy per second. So this is the additional rate of energy consumption for walking versus sprinting up the stairs. That was more than you asked for in that problem. You're welcome. I'll spend less time on the next two. The next one, well, this is kind of fun. We have one that's in English units. We have a pump that's measured in horsepower. And the question is, how much water can an 8 horsepower pump lift 3 meters in 10 minutes? So basically, we've got some kind of a water pipe. We've got our pump. This is a symbol for the pump, by the way. And the pump's going to lift the water uphill to a higher location. That height increase is 3 meters higher than it was before. So the water is going to be gaining some potential energy. So the water comes in this side and the pump lifts it upward. And we're basically told how powerful the pump is. So we look at our power equation. Power is work divided by time. And it's very much like the guy climbing the Empire State Building. The water isn't gaining speed, but it is gaining height. So as the water is lifted upward, the work done is just the potential energy that's gained as the guy climbs up the steps. So we could think about this in terms of the work done by the pump, or we could just say, hey, it's the amount the energy has changed by. How much has it increased or decreased by? And it's increased by the height. So our power is 8 horsepower. So P is 8 horsepower. The potential energy increase is mgh in some time t. So we're going to plug our numbers into this. This is the work or the energy change divided by time, and this is our power. And we're trying to solve for how much water. We can solve for the mass. How many kilograms of water are lifted? I have to be careful with my units, though, because if I want to get kilograms of mass, then I need this to be in watts of power. So I'm going to do a little unit conversion. I gave this to you on the previous page. So 1 horsepower is the same thing as 746 watts. So if I multiply 8 by 746, then I'll know how many watts of power this motor is generating. And then that's going to be equal to M times G times H, which is 3 meters, divided by T, and it says 10 minutes. And 10 minutes is the same thing as 600 seconds. So again, make sure your times are in seconds and not in minutes. And we can solve for the mass of water that this pump can lift. And maybe you're trying to pump your basement out and you're going to run your 8 horsepower pump. You're going to lift water out of your basement. Maybe it's flooded and you're going to run it for 10 minutes and you're wondering how much water you're going to pump out. Well, you could calculate it this way. You're going to pump a lot of water out. 122,000 kilograms of water would be lifted by the 8 horsepower pump. Okay, that leads us into our final question. Another place where power comes up in everyday life is how energy is billed, or how you pay for it. When the electric company charges you for electricity, they bill you in terms of the watts that you use and the time at which you use those watts. So specifically here, we're told the electric company is charging 12.4 cents per kilowatt hour. How much money could you save your dad? Why do I bring up dads? Because dads just have a thing about turning lights off. If your dad's like mine, or you're like me now that I'm a dad, Kids leave lights on, that just makes something go off in the dad's head. Okay. How much money could you save your dad by turning off a 100-watt light bulb for an hour? Because if you could figure out how much you could save him, maybe you could be a total smart aleck and just hand him that amount of money and say, I'm going to leave it on. Good luck. I'm not sure if that'll fly. So how much money does that represent? So we have to understand, first of all, what the heck is a kilowatt hour? That's what we're being told. And because each kilowatt hour is costing us 12.4 cents. So first of all, we got the metric prefix kilo, and kilo means 1,000. So a kilowatt hour is the same thing as 1,000 watt hours. 1,000 watt hours. Now, what is a watt hour? It's a unit of power multiplied by a unit of time. Now, the hour isn't the base unit for time. The second is. So let's multiply this by 3,600 because there's 3,600 seconds in an hour, and we'll get watt seconds. Okay, so this comes out to be 3.6 million times 10 to the 6 watt seconds. And a watt second, what we have here that the power company is billing me for, isn't actually power at all. They're charging me for power being used for a period of time, power multiplied by time. So what is that exactly, power multiplied by time? So think about your power equation. Power is the rate at which energy is being converted or work is being done divided by time. So if I multiply both sides of that equation by t, the t cancels out over here, and I get power times time, which is what this number is. And power times time is just an amount of energy. A watt times a second is just a joule of energy. So really what we're saying is that the energy being used that they're charging me for is every 3.6 million joules of energy. A watt second is the same thing as a joule. Costs 12.4 cents for every 3.6 million joules of energy. Okay, great. So I should be able to figure out, if I know how many joules of energy I'm using, I should be able to figure out how much money it's costing me. So let's go to our power equation. Power is energy per time. And we're told that our light bulb is 100 watts. So that's the power. It's consuming 100 joules of energy per second. And the question is for an hour. So an hour is the same thing as 3,600 seconds, so 60 times 60. We figure out how much energy this light bulb consumes. So multiply by 100, the energy consumption, so 3,600 multiplied by 100 is 3.6 times 10 to the 5th joules. So that's how much energy I'm using, 360,000 joules of energy, and every 3.6 million joules costs 12.4 cents. So if I divide my cost, I've got my energy per cost. This is really just a tenth of what cost me 12.4 cents. So this amount of energy only costs not 12.4, but 1.24 cents, which is the answer then. So if you totally wanted to be a smart aleck to your dad and you wanted to leave your bedroom light on for a whole hour, it's really only going to cost about a cent. You could give them 2 pennies if you really just want to, you're feeling generous. Now, if you leave it on all day, it comes out to be about 30 cents. And if you leave it on all year, they're really pushing things. It could cost you upward to about $100. But you really need more than one light on for a while to start adding up to any significant amount of money. That finishes all of our example problems. Hopefully that's helpful to you. Enjoy yourself with the homework and have a powerful rest of your day.